Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 12, part of this playlist that I'm calling Tests on Covariance Matrices. And let's jump to today's test, which is one sample test for sphericity. And what that means is we're testing whether the covariance matrix is a diagonal matrix with a constant variance. And so the variables independent basically, or are they not? Now, the hypothesis is that the variables are independent and have the same variance. And so really these should be bold letters, which I will change on the printed version. So are they multivariate normal with some mean and covariance matrix? Under the null hypothesis, the ellipsoid reduces to this, right? So if this is the diagonal, it's sigma squared I, the sigma squared, inverse, the sigma can be brought up over here, but this is the equation for a sphere. And so that's what we're testing. And the likelihood ratio test is this, which makes perfect sense because we're testing, look at the ratio of the sample generalized variance, S, versus the sample total variance. Now, if the null hypothesis is true, those should be equal. And if the alternative is true, then the numerator should be much larger than the total sample total variance versus the sample generalized variance. It can be shown that -2 times the natural log of R is approximately chi squared with 1/2 p plus 1 minus 1 degrees of freedom. The minus 1 is because we have to estimate the sigma squared. Now the test statistic can be expressed in terms of the eigenvalues of S. And so here's our test, the likelihood ratio test, and then we'll derive this and then we'll jump right into R and do a couple examples. So -2 log likelihood ratio is this. Well, the p raised to the p we bring to the numerator, and then we're left with this. But the determinant of a matrix is the product of the eigenvalues of that matrix, and the trace of a matrix is the sum of the eigenvalues of that matrix. So the test statistic can be expressed in terms of the eigenvalues of S, which is, I think, kind of cool in itself. So let's look at an example. And the data is from an FTP site that is, I think, freely available, or at least that's what I'm going on. And we're going to use data that's called bone data. It's not .dat, so I'll fix that too. And it consists of measurements 1, 2, 3, and 4 of the ramus bone for 4 different ages on 20 different boys. So each boy is followed for, at year 8, 8.5, 9, and 9.5 years old, and then it's measured. And so one thing we want to know is, are the means the same at each of these times? And so that should actually not be bold, and I'll unbold it in the printed version. But can we do a one-way ANOVA test? That's a question. Can we assume these are equal or not? Now, anyone with a statistics background knows that there's probably going to be a violation here because each boy is followed for 6 months, so it's the same boy across time. So these columns should not be independent. But we'll do a test to see if the covariance matrix is the identity matrix. And if it is, then we can do a one-way test. But if it's not, then we're going to have to use another approach to test, are the means at each of these time points the same or not. And we'll use Hotelland's t-squared for that. Specifically, what's called a one sample profile analysis of that. But first, let's do the ANOVA, or the test for sphericity. So it's in this library called multivariate tests, MV tests, and we load the data and we name the columns, and let's do the test. So it's called B sphere. That's the function in this package, and we load the data, and so we don't want the first column, and the test pumps out a very small p-value which says the variables are not independent. And if we look at the sample covariance matrix, there's a high correlation between time points. 8 year and 8.5 year, it's a 0.97, correlation. 8.5 to 9 years, so it's not surprising that the covariance was not diagonal, and the test shows that. So one approach to test the hypothesis, are the means equal across time, is to use what's called a one sample profile analysis, and we create a matrix and then transform our data, and then that's equal to this null hypothesis that they're all equal, or at least one of them is not. So we create this matrix. It's a contrast matrix, and each row the coefficients sum to 0. So we take our data times this contrast matrix, and then we do a one sample Hotel t-squared test on our new data x, and we're seeing if the mean vector is 0, and the test is really small. So that tells us that the means of the Ramos bone at years 8, 8.5, 9, and 9.5, the mean is different in there somewhere. And then so you could conduct tests to see at what point, is the means different, but we're not going to do that this test. Okay, well, that's all I have for this video. I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.